Okay. Now, the topic we're getting into today is, well, it's one of my favorites, but I think it's one of all of you have been exposed to some extent by me for some other purpose, like KSS or 685 or something. So I might not even need to do all this, but I will anyway, just because this is one of your topics. Oh, I'm over today because I traveled yesterday, and which always leaves me feeling useless the next day. And ugh. Okay. Um, so, yeah, so this textbook breaks it down kind of weird. We covered numerical integration, and then it takes a break to cover orthogonal polynomials, then it comes back to numerical integration. For Gaussian quadrature, generally yes, unless your function is periodic. Okay. Um, so, what we saw before is that if you have an n-node Newton-Cotes rule that has degree n minus 1 or n, depending on how many, whether it's an odd or even number of nodes. So in other words, if you have equally spaced nodes, which is what Newton-Cotes is, you can integrate polynomials of up to degree n exactly. But the thing is, every quadrature node has, I should say, n node quadrature rule has 2n parameters. Because what you're doing is you're approximating your integral using this combination of nodes. So you have to pick n nodes. And then you also have to pick n weights. So those are your 2n parameters. So you can choose those however you need to get as much accuracy as you can. So to maximize the degree, what we can do is we can set up equations saying, like, if we plug in f to be polynomials of increasing degree, 1, x, x squared, x cubed, and so forth. So if x equals 1, that just means we're going to get the sum of all the weights. And that should equal the integral of 1. Okay. I could really use some better chalk. Nothing but nubs. Okay. I'm going to get something from my office. Oh, I heard from Vivian. Oh.
No, that was me.
No, but Vivian texted me.
Oh, okay.
All right. It is going on tape. I figured Brianna would tell you in class.
Well, I didn't know she wasn't coming to the meeting. She said she may know.
I got home late today from traveling, needed some rest.
Yeah.
Okay. Okay. All right. Good.
But I thought she was coming to the meeting. So
Ah.
I was like, where is she?
Haley. That's all your comment. Okay. So now if we move to the next, x, that'd be w1 x1 plus w2 x2 all the way up to wn xn, and that should be the integral of x. And we would just keep going. And the thing is, we have 2n unknowns, all the nodes and all the weights. So we can set up 2n equations. So we can keep going until we have 2n equations. So that would be x to the what?
Is that supposed
Is
to
that
be
x or x squared?
at the
X.
Okay.
So I could go all the way up to x to the what? 2n minus 1. So I can have 2n equations, because I'm starting at x to the 0. Okay, so x to 2n minus 1. So w1 x1 plus w2 x2, all nodes raised to the 2n minus 1 power should equal the integral of x to the 2n minus 1. Okay. Another thing is, if we set this up to if we set up AB to be a symmetric interval, that would be especially convenient because that means all the ones for odd powers of x, those integrals would be 0. So I think, okay, 2n equations, 2n unknowns, and we just solve for all the nodes and weights. And so 2n minus 1 seems like the best that we can hope for because that's all the flexibility that we have. So you might think, oh, okay, let's just solve this system, and we're done. And we've maximized the degree, except there's one big problem. How do you normally solve a system of n equation, 2n equations and 2n unknowns? What would you do? How would you solve a system of however many equations and same number of unknowns? Gauss elimination.
Elimination.
Yes, that's the word you were looking for.
Yeah, thanks.
Yes, but something like Gauss elimination applies to what kind of equations? Linear equations. Yeah, so they do linear in whatever unknowns you have. Our unknowns here are the weights and the nodes. Are these linear equations? No, because first of all, you have unknowns multiplied together, so that's a no-no. And you have unknowns raised to powers, also a no-no. So this is a system of nonlinear equations. And yeah, there are techniques for solving them using analogs of Newton's method and things like that. But if we could find an easier way to proceed, that would be preferable because okay. Because how difficult a system like this is to solve, it just depends on what your coefficients are, because algebraically it could be extremely challenging. Now, I have solved this system in a case where you just have just 2 nodes. And so if you have, so n equals 2, so you have 4 equations in the 4 unknowns, the 2 nodes and the 2 weights. That can be done. I've never tried to go any further than that. It may not be possible to do it by hand, although, as we'll see later, you can actually look up the answers, so it has been worked out. Okay, so we'd like to find a different approach to find these magic nodes and weights that give you as high a degree as possible. Now, so this approach, even though it's not really pursued, it does have a name. This is called direct construction. Of this kind of quadrature rule that maximizes degree. Now that is a Gaussian quadrature rule, but I haven't properly introduced it to you yet. But so conceptually, it's the simplest approach because you're just setting up equations and solving them. But it's just the equations are really hard to solve. It is also called moment matching. Because these integrals of powers of x, these are referred to as moments, similar to moments from physics. Because you can think of like the first moment dealing with x to x of a first power, that's like an expected value. Second moments are related to variances or standard deviations and so on, but also related to like moments of inertia, center of mass. So first moments give you center of mass, second give you moments of inertia, tendency to rotate, things like that. So so it's based on the moment in the physics sense. Because what you're doing is these are the exact moments for your for this measure for your integral, and you're trying to match them against the moments you would get from your quadrature rule. So you're just requiring a certain number of moments between the integral and the quadrature rule agree. That's the term moment matching. Okay. So what we do is take a different approach to try to find out how to get the nodes and weights that would work best and maximize the degree. Okay. So what I'm going to do is, and I'm honestly not sure why I used G in the notes, but I'm just going to go with it. So I consider G is the space of polynomials of degree 2n minus 1. So space of all polynomials of that degree or less. Okay. So I can define G n minus 1 to be the interpolant of G at my nodes, which are not yet chosen, but we're going to use this to try to figure out how they should be chosen. Okay. Now, I'm going to approximate my integral of G to be, so if I set my quadrature rule as and I'll just use this as an interpolatory quadrature rule. In other words, once I've pinned down the nodes, I'm just going to use the weights that would normally follow from using those nodes. So each weight is the integral of my Lagrange polynomials with respect to these nodes. Okay. So my exact integral is equal to my quadrature rule plus my error. My error is going to be the integral of my exact integrand minus my interpolant. Because when you're using interpolatory quadrature, what that means is your quadrature rule is equal to the exact integral of your interpolant. So really all I've done is I've taken my exact integral and I've added and subtracted the integral of the interpolant. It's just that I'm taking this one to be my approximation and I'm using this one to define my error. So what I want to do is, I want to find out how can I make the error 0. Now, G is equal to Gn minus 1 at all the nodes. Okay. So what that means is I can partially factor the difference between them. So G minus G minus 1 is equal to a product, x minus x1, x minus x2, because this is a polynomial of degree at most 2n minus 1. And now I know n of the roots. Okay. So I have this part that's of degree n, because all the nodes are distinct. And then I'll have some remaining part, and this has degree n minus 1, because the whole thing has degree 2n minus 1. I've taken out n factors, so n minus 1 is all the degree that's left. Now, in the interest of making this equal to 0, well, not this, but the integral of it to be 0, I now have, based on what I was covering up to this point, last week, how to choose the nodes. So, if I define the sequence of polynomials, so these are like my orthonormal polynomials. On the interval AB. So basically we're falling back on all the material I just covered. So we can generate this sequence using Gram-Schmidt orthogonalization, or really the free-term recurrence relation. So we've been over all that, so I don't need to go over that again now. So what I do is I can choose my nodes for my quadrature rule, x1, x2, up to xn, to be equal to the roots of Qn. What that means is my error in my quadrature rule, which is the integral of g minus gn minus 1 minus c turbulent, and that is the integral of x minus x1, x minus x2 up to x minus xn times the rest of it. Okay, but now what we have is okay. You know what? I'm going to use something else that I defined last time when I first covered orthogonal polynomials, and that is, these are the normalized ones. I also had the unnormalized ones. P0, which is equal to 1, P1, P2, etc., are orthogonal. And whatever property did they have? Does anyone remember? Instead of being normalized, like to have the magnitude of 1, what, What convention did they follow instead?
Wait, are you talking about them being orthonormal or something?
Well, Q's are orthonormal.
Okay.
The P's were not. They're just orthogonal, but we had so instead of having a convention that they have norm 1,
Yeah.
they followed a different convention, which is also convenient. What else was equal to 1 instead?
So,
So you can play Where's Waldo in your notes. I don't think they were in my printed notes, but like what I wrote on the board.
Morning?
Yes. They're monic. Does anyone remember what monic means?
Yeah. Sorry.
Okay. They have leading coefficient of 1.
oh.
Yeah. That's why we could find the first one and just be 1, and then keep going from there. Okay. Okay. So I'm going to use that instead, because that's actually more convenient. So it doesn't matter, as far as roots, they have the same roots, obviously. So I can use the roots of Pn or Qn, they are the same. Okay. So that means this right here, this is Pn. That's why I made the switch. Okay, so what is this though? This is the inner product of Pn, orthogonal polynomial of degree n, with this polynomial Rn minus 1, which is a polynomial of degree n minus 1. Well, what must that inner product be?
Quadrature delta n minus 1.
No, but
0.
must be 0, because this polynomial is orthogonal to all polynomials of lesser degree. Okay. So the error is 0. Therefore, the quadrature rule is exact. So those are the magic notes, if you will, that give that such a high degree of accuracy. Whereas just any other choice of nodes would generally give degree only n minus 1. Okay. Now, so now I can define a Gaussian quadrature rule. So if I have on whatever interval AB, my integrand f, and then I might have an optional weight function, wx. I didn't already using one before, but all the same discussion would apply. Is equal to, well, approximately equal to f evaluate these nodes and the weights. So the nodes are the roots of a polynomial Pn of x, such that the integral, the inner product of Pi and Pj, which is defined to be the integral of their product with the same wave function over the same interval AB, must be equal to 0 if I is not equal to j. So that's what characterizes the nodes, that they're just roots of a polynomial from a sequence of orthogonal polynomials. And then the weights are the integrals of the Lagrange polynomials for the nodes with respect to the same weight function over the same interval. Now, what do we know about roots of orthogonal polynomials? So, it's actually something like one of the last things I proved about them before we wrapped them up. Because it would be kind of strange if we go ahead and get this orthogonal polynomial, we get its roots for an integral over AB, and we get roots that are complex.
They're always real.
What?
They're always real.
Yeah, and that's what I proved last time. Yeah, that they're real, they're distinct, and best of all, they're in AB. So they make perfect sense to use as quadrature nodes. I mean, yes, technically you can do quadrature using nodes that are outside your interval. It'd be kind of strange, but it's theoretically possible. But here, there's no need to even think about any problems from that. Okay, so so this rule is exact if your function f is in a space of polynomials of degree 2n minus 1 or less. Okay, so because it has a much higher degree of accuracy than general quadrature rules, you can they're generally much more accurate for in most cases. There are exceptions, like in periodic functions, the composite trapezoidal rule is still the best, but Gaussian quadrature is definitely most popular in real applications. But there's one problem, well, not the only one, but one of the main problems with Gaussian quadrature rules is they require roots of polynomials. And finding all the roots of a polynomial, especially of higher degree, is not necessarily easy. You might think, okay, how do you find the roots of such a polynomial? You can use like Newton's method or any other root finding method to get them. At least you know they're in the interval AB, so that helps. But the higher the degree, the harder that is to do. Fortunately, for most reasonable cases, you might not be using too many nodes, and you don't really need to find the roots yourself. Well, in most cases. So, so to get to nodes, and even the weights, for a general interval AB, and at least for a weight function equal to 1, here's what you can do. You can actually look up all the nodes, which I'll call, let's see, I want to call regular nodes xi and wi like I have been, so these come up with different names. I'll look up nodes, I'll call them ti and the weights si for the generic interval -1 to 1. In a table. You can find tables, in books or online for Gaussian quadrature nodes up to like however many decimal places, because due to floating point precision limits, 15 or 16 decimal places is all you could really ask for anyway. So those nodes are published. You go to Wikipedia page and get the first few, but if you need more, I'm sure there are tables online that list them to however many decimal places. So that has been done, at least for its generic interval. And then what you can do is basically you shift in scale to your general interval AB. So first I'll show the weights because that's simple. Weights, you only have to scale them. So your weights for AB, you can just take your weights for -1 to 1, divide by 2, because 2 is the length of -1 to 1, and then multiply by the length of your interval. So So that adjusts the weights for you. And then for the nodes, it's the same idea that, again, you're going to scale the nodes that you have. Okay, Ti. But this gives you nodes that are in an interval of a right length, but they're centered at 0, which you don't want. So you have to now shift them to the midpoint of your interval. Nothing to it. And so then you can then those will be your Gaussian quadrature nodes and weights for your general interval AB. Now, if you have a different weight function, you might have your work cut out for you. Like if it's a well-known weight function, well, for instance, for a weight function for like 1 over square root of 1 minus x squared, your orthogonal polynomials are the Chebyshev polynomials. There's a formula for the roots of those, so that's no problem. Other more esoteric weight functions, you might not have those available. But another thing you could do, there are techniques from numerical linear algebra that actually this goes into Amber Sumner's project that she's starting on it, that Megan Richardson did a little work on too. If you have Gaussian quadrature nodes for one weight function, how do you get them for another, and as efficiently as possible? And it depends on the weight function, but there are ways that are pretty slick algorithms for making those kind of modifications. That's a bit, actually, it's way beyond the scope of this class, but they're out there. Or you can just go ahead and do the Graham-Schmidt to get your orthogonal polynomials and then compute the roots by whatever means you can. This might be kind of a pain if you have a large number of nodes. So this is one thing that's rather inconvenient for Gaussian quadrature compared to other quadrature like Newton cotes or composite rules, because there it's really obvious what the nodes are. They're very simple formulas for them, and you don't have that in this case. Also, what if you want to like double the number of nodes? Well, all the old nodes are thrown out. You can't reuse those function values. So Gaussian quadrature rules they're not progressive. So as you increase the number of nodes, it doesn't mean you reuse the old ones. Okay. And I have an example in the notes where I show how you do the shifting and scaling for just for a simple case, based on the nodes from a table. Okay. All right. So. Okay, so cons. I mentioned the roots can be difficult to compute. Although those of you who've been taking my 685 or anything like that, you know that the Gaussian quadrature nodes can be eigenvalues of a tridiagonal matrix, and that they're actually easier to compute that way. But forming that matrix can be a pain. And then the other one just mentioned they're not progressive. So in other words, I'll put it this way. If I have the nodes x1, x2, up to xn for n node rule, those are not contained in the nodes for a rule of 2n nodes. So Gaussian quadrature rules of higher number of nodes do not build on those with smaller number of nodes. Now there is one alternative. And again, something that's beyond the scope of this course, but I just want to mention it. And those of you who are KSS might make use of this. Gauss-Kronrod rules. What they do is they are built so a 2n plus 1 node Gauss-Kronrod rule contains the n-node Gaussian nodes. So it's a way of extending a Gaussian quadrature rule into another rule with more nodes in a progressive manner. And bless you. So the purpose of Gauss-Kronrod is often used as error estimation for a Gaussian rule. Since at least you can reuse these n function evaluations, and then you have relatively little overhead on top of that to get hopefully a decent error estimate. Okay. And that actually takes me, wait, how am I doing on time? Oh, okay. Okay, did that. Oh, okay. I'm actually just about out of notes. I didn't expect to get through all that. So I want to make sure I'm not leaving out anything. Okay. Well, because what I have planned for next time is, speaking of error estimate, we have error formulas for like trapezoidal rule, Simpson's rule, and so forth. We need a similar error formula for Gaussian quadrature, but I have that on tap for next time. But there's something else I'd like to show you, because you're going to think, okay, Gaussian quadrature is nice because it has such a high degree of accuracy. Yes, that's true, but it's one of the main pros about it. But there is one other that is just as significant, if not more so. Okay. And it has to do with the weights. All right. So, if I take the integral of one of these Lagrange polynomials, now that is known to be the weight, Wi. But now what I'm going to do, at least satisfy the property that each one of these, if I plug into the ith polynomial, I plug in xj, I get quadratic delta ij. So it's equal to 1 if I equals j and 0 otherwise. But now I'm going to do something rather strange. I'm going to integrate the same Lagrange polynomial squared. Now, the Lagrange polynomial by itself is of degree n minus 1 because it has n nodes. So, therefore, n minus 1 roots. If I square it, that's going to have to degree twice that, so 2n minus 2. But a Gaussian quadrature rule is accurate, is exact, up to degree 2n minus 1. So because this is less, this is actually equal to what I would get from applying the Gaussian quadrature rule to it. I need a different index here, xj. Okay. Polynomial I, node j. Okay. Times the weights. Okay, so normally I'd have to put an approximately equals here. But because this is low enough degree, I can say this is exact. Okay. But the thing is, Lagrange polynomial evaluated at these nodes is equal to this Quadrature delta. Quadrature delta ij squared. But that's equal to 1 only if I equals j. So, and some of you will know the answer to this already from seeing it before, but what is this equal to?
Wait, when I equals J?
Yeah, because we have this situation.
Oh, okay. Then it's
Just the weight.
Not wj,
or the sum of, wait.
because we're summing
The sum
over
of all
j.
the weights?
No?
Is
Oh, wait, wait. Okay, when I equals J.
W what?
W-I?
Yes, wi.
Oh, okay, that's,
I
I put W-J, but
I is a fixed
Okay.
index, j is varying. So j is going to
Cool.
count through all of them, and so you pick out the one j that equals I. Yeah, wi. Okay, now this seems a little odd because I just said that the integral of Lagrange polynomial squared is equal to the integral of Lagrange polynomial to the first power. Now, generally, that does not happen. But it just happens to be true in this case for nodes that are roots of orthogonal polynomials. Now, this is a formula that may be more practical to use, but this is a theoretical interest because what am I doing? I'm taking the integral of a function squared. If you integrate that, so what do we know about the value, the numerical value of this integral?
it's positive.
Has to be positive. And we like having quadrature rules of positive weights. They are numerically stable. This is the downfall of Newton-Cotes rules. Because with Newton-Cotes rules, once you get to a certain degree, like degree 11 or so and higher, you are going to have at least one negative weight, and therefore they lose accuracy. But Gaussian quadrature, that's never going to happen, no matter how many nodes you have. That you're always going to have these positive weights. And what that actually means is the limits as n goes to infinity of your Gaussian quadrature rule computed for the appropriate number of nodes, it's actually going to converge to the exact integral. I'll prove that later on. So this is something that actually does not hold for Newton-Cotes rules. The proof of this result is dependent on it's dependent on all the weights being positive because it deals with the bound involving the absolute value of the weights. And if you can't bound that because you have certain weights being positive and negative, then you can't prove this convergence result. Okay, yeah.
I have a problem when weights are negative. What does that mean? I cannot feel it. To me, it doesn't make sense. Must be positive.
You'd think so, yeah. But the thing is, for an interpolatory quadrature rule, any interpolatory quadrature rule, your weights are just going to be the integrals of these Lagrange polynomials for whatever nodes you chose. And it just so happens that, for instance, if you choose the nodes to always be equally spaced, and these integrals are free to be positive or negative, because these are oscillating polynomials of whatever degree. So, and because we saw for simple rules like trapezoidal or midpoint or Simpsons, all those weights are positive. It's just that when you get to high degree, things go badly. So, because if you think in terms of a Riemann sum, that makes no sense. It's like you have a rectangle that's really like oriented the wrong way, and another compensated for by a rectangle that's too big. So, so this is one of the risks with numerical integration, but you have to pick your notes carefully, or you might get a surprisingly inaccurate result. It's physically ludicrous, but it still happens.
Is it possible to draw like example?
I'll try.
Thank you.
So here's your integrand, and let's suppose we have some nodes. Okay, so let's suppose I'll make weight 4 be the negative weight. So now the sum of all the weights has to be equal to b minus a, no matter what, for any interpolatory quadruple. So for instance, I might have, so the weights will be the widths of my rectangle. So here's like W1, and, well, whoops, the function value at the node determines the height. So f of x1 determines the height of this rectangle. I've never actually tried to draw this before, so this is going to be interesting. Okay, so here's so this width is W2, and then say W3. Whoops, I keep getting the heights wrong. Okay. All right. Now, okay, so here are my heights, f of x4 and f of x5. So far, everything's as you'd expect. You have these disjoint rectangles with heights coming from the integrand. So the height of this is f of x2, for instance, f of x3. So you have a situation where the weight, if W4 has a negative weight, that means that W5, though positive, ends up being too big. So I might have a rectangle associated with f of x5 that maybe spills over into this space. So we have this W5 that is the width of that rectangle that is way too much. And therefore, if I were to add up these four, I'm going to have a total width that is greater than b minus a. So now what I need to do is offset this. So the width of this portion, this overlap, is going to be minus W4. So now what I can do is, so then I can make sure that W1 plus W2 plus W3 plus W4 plus W5 still has to equal b minus a. But this rectangle that has this negative width will still have this for a height, because it's W4 associated with f of x4. So, in other words, the result I'm going to get for this, who knows what it's going to be.
But, I mean, this is kind of fancy one, because we cannot have a rectangular larger than, like, h. This is kind of, I don't know, 3h in compared to the others.
It's kind of what?
In compared to others, like the x1, x2, x3.
Yeah. Oh, yeah, I just figured to illustrate how you could have a negative weight.
Okay.
Yeah, well, actually, I think I might have, oh, I do have MATLAB open. I'm going to see if I have a function handy for this. Because I know I've written functions that compute whatever Newton-Cotes nodes and weights. I just don't remember where I put these things. Okay. Quad interp weights. Okay, so if I give it the weights from -1 to 1, however many there are, it will, okay, So I'm going to give a bunch of equally spaced points for Newton-Cotes rule, for instance, between -1 and 1. All right, so -1 up to the spacing 0.1 up to 1. So let's see what that does. So that's going to be 21 nodes altogether. Oh, wow. Okay, so if I were, so keep in mind, the interval -1 to 1 has a width of 2. So you'd think, okay, you should get a bunch of positive weights and you add them up and you get 2. So here's what happens. So to give you an idea of how bad it can get. So the weights for Newton-Cotes 21 nodes, and it's closed, meaning a closed Newton-Cotes rule includes the endpoints A and B. And just to make sure this is right, because these numbers are out of this world, I'm going to add them all up. Yeah, I get 2. So here are what the so starting from left to right. So I get 0.0237. Okay, that's fine. Then 0.2283. Although you figure if you have 21 weights for an interval of width 2, you think each weight on average should be about 0.1 or so. But we're already getting more than its share. Then the next one is minus 0.4730. So now we're in the hole. And then
Was it because of overlap? The negative sign?
Well, but then it gets out of hand. So now we're one weight wider than the width of the whole interval.
I mean, it is strange for me. I really like to see if there is any figure here.
Any what?
Any kind of figure, just to show
That's
how
bit
it's
visualized?
calculated.
Yeah, because it just keeps getting worse. In fact, the largest weight that I get is up to minus 180. Yeah. So this is why we don't use equally spaced points at high degree. Now, if I cut back a little bit, like say 0.2 spacing, so 11 nodes, it's a lot better, but you still have, there's 2 weights that have like minus 0.87, so almost half the width of the interval, that are, whereas all you'd have to do is choose a Chebyshev points and you'd have positive weights again, just because of orthogonality. So yeah, how to interpret that visually, it's almost like what you'd have is, like for a case like this, you'd have these crazy rectangles spilling way past AB, and that would have heights determined by your integrand, and they would just be overlapping each other.
So I just thought if that figure that you draw, just a little more condensed.
Yeah, because I was thinking like, okay, maybe for negative weights, maybe just a little bit negative. I honestly wasn't expecting this. So, yeah, but this is what happens when you allow the weights to be pretty much whatever, and you don't impose a constraint on them. So, see, that's why orthogonal polynomials are so nice, that we don't have these things that we can't figure out. So, okay. Now, I really don't have anything more to cover today, and I would call on somebody, but I just don't feel like it. You already went, right? And Vivian already went. Okay, that leaves, so, yeah, and, she's not in the class anymore. So, you two, okay.
To be honest, I haven't even worked on the homework, so I'm trying to do the midterm. Since I started working on the midterm. What chapter?
Well, see, the last one I did was chapter 6, right? Or, okay, so. Okay, all right, that's fine, because I don't want to do chapter 8. And I only finished recently chapter 9. Okay then. Good. Then I could just stop this and upload this video and get home earlier. So.